every cyclic group, okay, every cyclic group is either Z or Z mod Nz, which we can write as Zn. When you pursue higher studies, this means something else. Yeah, and people usually denote this by Z mod Nz. Some confusion might arise when you look at Z, but it's okay for the time being. Then, what is an abelian group?
It follows the commutative
A
property.
group satisfies commutativity.
Yeah, so the order of operations doesn't matter. If you multiply A with B or B with A times B, B times A, it gives you the same thing. That's called an abelian group. What are some of the examples of abelian groups?
K4 group.
Yeah, K4 group is one interesting example, which is not cyclic, but is abelian. It's one of the first ones.
Q plus
What else?
K3.
Q.
Yeah, rationals. Then somebody said
Zn.
A3, but E3 falls under cyclic groups, right? A3 is Z mod 3Z, Z3.
Yes, sir.
Yeah. Turns out, if your abelian group satisfies some finiteness conditions, then it's essentially a combination of Z and Z mod NZs. So for instance, K4 is a finite group. So I'm saying K4 should be written as a direct sum of these, and we'll see what a direct sum is. But for those who know, this is V2 direct sum Z2. This is the only other group of order 4. Okay, everybody knows what abelian group is now?
Yes, sir.
Yes, sir.
What about non-abelian?
Q8.
Yeah, but what does a non-abelian group mean? The
There
obvious,
exists
it's not
A
abelian.
star
There
B
exists a
not
pair
equal
which
to B star A for some AB belongs to the group.
Right. So the negation of what you had over here, non-abelian. So everybody knows this. So what's an example of a non-abelian group?
Matrices under multiplication. 8.
Yeah, which matrices?
Generally,
General linear.
multiplication.
Yes. So GLN of any field or any ring. Those are examples. What's the first
Permutation.
example of a non-abelian group?
S3.
Yeah. So S3, if you write down all non-abelian groups, order them by cardinality, S3 is the first one. Yeah. We'll see what how to simplify S3. Okay. So now, next definition, subgroup. So can somebody tell me what a subgroup is?
A subset of group which follows the same conditions.
Yeah, a subset of a group which follows the same condition. So a subgroup H, which is denoted by this symbol less than or equal to G, is a subset which is a group by itself. Okay. Now, one of the first theorems which you see when subgroups are introduced is Lagrange's theorem, right?
Yes, sir.
So can somebody tell me what does Lagrange say about subgroups?
The order of the element divide
If
order of
H
group.
is a subgroup of group, then order of H must divide the order of group.
Yeah. So if H is a subgroup of G, both are finite, then order of H, which makes sense because things are finite, divides order of G, which makes sense because things are finite. Okay. Some other statement of Lagrange says that G can be written as a disjoint union of cosets of H, and the finite avatar of that theorem says this, that cardinality of H divides cardinality of G. Okay. So what are some of the examples of subgroups?
A special linear group is a subgroup of general linear groups.
Yeah, so SLN over. So when you say general linear or special linear, you should specify over what? So SLN of?
Zn
Okay.
from R.
One can take Z or R. This is a subgroup. It's a subset, but in fact, it's a subgroup of GLN of Z. Okay. Yeah. So next definition, homomorphisms. So what are homomorphisms?
Mapping which satisfies the condition that phi of AB is equal to phi of A and phi of B.
Yeah. So homomorphisms appear everywhere in mathematics. Whenever you have a structure on a particular set, you can talk about homomorphisms. And homomorphisms are maps which respect the structure, right? So you can look at G, a group, and G prime, a different group, and a set theoretic map between them. But set theoretic maps are not that interesting, right? Because you have group structures on both sides. So we put the assumption that this map respects the group structures. So A dot B is mapped to f of A times f of B over here, if this set theoretic map is F. Okay. So one interesting example of homomorphisms is subgroups. Right? If you start with a subgroup H of a group G, then the inclusion map from H to G is a homomorphism, right? So that's one of the interesting examples.
Excuse
And,
me, sir.
Yeah.
Can you please move the screen a bit to the first slide? Actually, I wanted to
Yeah.
copy the definitions down, but couldn't. Thank you, sir.
Yeah. So homomorphisms. So associated to homomorphisms, there are many concepts, right? So what is the kernel of a homomorphism?
X belongs to G such that f of x equals to 0.
Okay, yeah. So somebody was answering, but their mic was too low. So please turn your mic up. So X in
X
G
belongs to
such that,
G such that f of x equals to 0.
yes, is the identity in G prime, which I'll call E prime. Okay, so that's kernel. Now kernel is a subgroup of G, right?
Yes, sir.
Yes,
Okay.
sir.
It's a subset because it looks like it, right? All X in G such that something happens. So it's a subset, but in fact it's a subgroup. Next, what is image of F?
Y belongs to G prime such that f of x equals to y.
Yeah, Y belongs to G prime such that we are mathematicians. We need to be extremely precise. We should say Y in G prime such that there exists an X in G such that Y equals f of x, right? You cannot just say Y in G prime such that Y is f x. You need to say there exists. This is image F. Now, image F is a subgroup of what?
G dash.
G dash, right. So image F is a subgroup of G dash, kernel F is a subgroup of G. So now some excursion into people who might know things. There is a concept called as co-kernel of F, which you'll encounter in your higher studies. and it is defined to be G prime modulo image of G prime, sorry, image of F when things make sense. It doesn't always make sense because image F may not be normal, but yeah, you can look at G prime mod images when things make sense. Now, this leads into automorphisms. So what are automorphisms?
Isomorphisms from same
The
name
set
group.
of bijection map from a group to group.
Yeah. So now that we have homomorphisms, we can put some set theoretic conditions on the maps, right? That the map needs to be injective, the map needs to be surjective, and whatnot. So if we put both of those conditions, injective plus surjective, which is bijective, we get an isomorphism, right? Now, if both groups are the same, G to G, if you have a map F, which is a homomorphism plus bijective, then F is called an automorphism. Okay. Yeah. So what are some of the examples of automorphisms? Some interesting ones. Don't say identity.
F of x equal to minus x.
Yeah. So what is your group?
Integers.
Integers. Okay. Z to Z, you are taking the map sending x to where?
Minus x. Minus x.
Yeah, minus x. So this is essentially the only non-trivial automorphism of Z. Okay. Now, the set of automorphisms of a group form a group by themselves. Okay. So you can look at aut G. It's a priori just a set. It's a set of maps from G to G, which are homomorphisms and bijective. But they form a group structure. Can somebody tell me what's the operation over there?
Function composition.
Uh-huh.
Function composition.
Composition of
Yeah. So composition of maps. That's the group operation over there. One can check that it satisfies all the properties, associativity and whatnot. One cannot expect this to be abelian, may not be abelian, but yeah, it's a group coming out of a different group. So this is a construction starting from a group, how to get a different group. You take aut. Sometimes aut is trivial, sometimes aut is non-trivial. Sometimes automorphisms of huge groups is small, just like you saw over here. Aut of Z is just a two group, right? So there's that. What? Is there a question? Okay, fine. So maybe I'll move this. Now, now comes the important part, how to construct some additional groups out of groups that you already know. You have done that before. So starting with G1 and G2, one can look at the set G1 cross G2. Can somebody tell me what is this set? What this set is?
Ordered pair A, comma B.
Yeah,
Does
it's a
that
set of ordered pairs A, comma B, where A is in G1 and B is in G2. So can you turn this into a group? Can you turn G1 cross G2, the set theoretic Cartesian product, into a group? The answer is yes. What you do is you have the operation on G1 and the operation on G2. Just take the product of those two operations. So the group coming out of this Cartesian product is called the direct sum of G1 with G2. Since you'll ask why it is called a direct sum and not a direct product, but turns out since there are only two groups, they both agree, the direct sum and direct product. If there are infinitely many groups, then they may not agree, the direct sum and direct. Is this fine? This construction, starting from two groups, G1 and G2, you can take the Cartesian product of their underlying sets and give it the component-wise product operation that will give you a new group.
Can you give a example?
Yeah. So the example was already on the last page. You start with Z mod 2Z, Z2, take a second copy of Z2 and take the direct sum of those. So this is set theoretically 0, 0, I won't write bar, 0, 1, 1, 0, 1, 1. Is that okay? That this is the set theoretic Cartesian product.
Yes, sir.
Okay. Now let us write down the operation table of this. Zero, 0, 1, 1, 0, 1, 1. This is 0, 0, 0, 1, 1, 0, 1, 1. Okay. So what it's common sense. What can be 0, 0 dot 0, 0? So what's your guess? The naive guess is the answer. Let's call this plus. So what will you assign 0, 0 plus 0, 02?
0, 0.
0,
Yeah.
0,
Then what is this?
0, 1.
Yeah. What is this?
1, 0.
Yeah. Just say everything. I'll write those down. What's the next one?
1,
1, 1.
Then?
0, 1.
0, 1.
Then?
0,
0, 0.
Yeah. It should be 0, 2, but it's Z mod 2Z. So it wraps back to 0.
And 1, 1.
1,
1, 1.
1, 0.
0.
1, 0. Then?
1, 0.
1, 0.
1, 0.
Just a minute. 1, 0. Then?
1, 1.
1,
Yeah.
1.
0, 1.
0, 0.
0. Huh.
0, 0 and then 0, 1.
0,
Then?
1.
This should
1,
be.
1.
1.
Oh, just a minute. My tablet powered off.
1,
But
1.
yeah, you can see.
1,
What?
1.
Yeah, just a minute. It's starting. Sorry for this. Is this back up?
Yes, sir.
Yeah, it erased the entire diagram, but you got the idea, right?
Yes, sir. Definitely.
So component wise, you have to do those operations. Maybe this is a way of my iPad saying, redo this exercise all by yourself again. But yeah, so this construction of getting a new group out of the two old groups G1 and G2 is called the direct sum of G1 and G2. Okay,
Okay, sir.
direct sum or direct product. So let us look at a slightly twisted version of this. So suppose you have G1 and G2. Okay, suppose you have G1 and G2 and a map, a homomorphism from, let's call it F, from, let's say, G2 to aught of G1. So given an element of G2, you have an automorphism of G1. Then you can construct what is called as a semi-direct product of G1 and G2, and it's the operation set theoretically it's the same, x comma y in G1 cross G2, but the operations are slightly twisted. So if you start with x comma y, then x prime comma y prime, then think of it this way. You are multiplying everything together, x, y, x prime, y prime. This is equality in quotations. You want to transfer x prime across y. So you can do that by writing it this way. Is that okay? Because I inserted x prime and x prime inverse in a fake way over here. So it cancels and you get back this. And you just replace whatever is inside the brackets with this f evaluated at, so I'll write it this way, x prime x prime and f of x prime evaluated at y prime. Okay, this construction is called the semi-direct product construction. This is slightly subtle, but we'll come to examples after this. But I just want you to see this. So now some examples.
Sir, can you please show up the screen?
Yeah.
Okay, sir.
Okay.
Yes.
I think I made a mistake over here. The indices should be the other way around. G1, G2. This should be the other way around. And now I think it makes sense. Is that okay? Yeah. Just flip the indices. Sorry. So example is S3. So I want to say S3 is a semi-direct product of Z2, I mean Z mod 2Z and Z mod 3Z, where the map F over here goes from Z2 to aught Z3 sending 1 to the automorphism. So the map sending x to minus x. Is this okay?
Yes, sir.
One can check that the resulting group is isomorphic to S3. Okay. So this leads us naturally into these groups S3, S4. So what is Sn, you might ask? So can somebody tell me what Sn is?
Permutation group.
Yes, Sn is the permutation group. It's the group of permutation of n symbols.
Yes, sir.
So it's set of all maps F from symbols 1, 2, dot, 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 n. You can call these anything. These are just symbols. To 1, 2, dot, 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 n, such that F is bijective.
Yes, sir. Definitely.
Yeah. So this is a set, but you again give it the standard group structure, composition of functions.
Yes, sir.
Then this set becomes a group and it's called Sn. Can somebody tell me the cardinality of Sn?
N
N
factorial.
N
factorial.
N
factorial.
factorial. Okay. So that's it. Yeah. Now, any such map can be represented by what is called as its cycle decomposition. So everybody knows what a cycle decomposition is?
Yes, sir.
Yeah. So suppose I give you this map. Let's say 1, 2, 3 going to 1, 2, 3, where 1 maps to 2, 2 maps to 3, and 3 maps to 1. Then what is the cycle decomposition of this
1, 2, 3.
bijective?
So
1,
1, 2, 3.
Yeah. So it's 1, 2, 3. So how do you read this? You start with 1, then 1 is mapped to 2. So then the next entry is 2. Then you look where 2 goes. 2 is mapped to 3. So the next entry is 3. Where does 3 go? 3 goes back to 1. So this cycles back to 1. So cycle decomposition. Okay? Everybody's familiar with this?
Yes.
yes, sir.
Okay, great.
Yes, sir.
Now, what are some of the subgroups of Sn?
An.
Yeah.
Or
So
So
An.
alternating groups.
Yeah. So what is An?
All the even
Even
permutation.
even permutation.
Yeah. So how do you define even permutations?
Those are right
Even
as
number of
even number of
transpositions.
transpositions.
Yeah. So one easy thing to say is you can look at the lengths of these cycles, but let's take this perspective, even number of transpositions. So what are transpositions? Can you tell me?
Two
It's
length
a
cycle.
cycle of two length
Cycle of
cycle.
length.
Length 2.
Yeah. So this is a cycle. Its length is 3 by common sense. But if it were 2, then it would have been called a transposition, right? Now, you said an element can be written as a product of even number of transpositions. So, what are you using? You're using the fact that every element of Sn can be written as a product of transpositions, right?
Yes, sir.
So, how can 1, 2, 3 be written as a product of transpositions?
1, 3 and
1, 3,
1,
1, 2.
Yes. So, yeah, this is 1, 3 times 1, 2. So how do you see this? That these are equal. So 1 goes to 2 and then 2 goes to 2. So 1 goes to 2. 2 goes to 1. 1 goes to 3. So 2 goes to 3. And 3 goes to 3 over here. But 3 goes to 1 over here. So 3 goes back to 1. So that's how we verify the equality of these two bijections between 1, 2, 3 and itself. Now, this element
put this.
Yeah, so I just checked this equality.
Sir.
I checked this equality by evaluating both sides at 1, 2, and 3. So if you evaluate the left hand side at 1, what do you get? This is a function, right? This is a bijective function. What is this function evaluated at 1?
सर एक्चुअली क्वेश्चन समझ में नहीं आया.
So this is a cycle which corresponds to this function, right?
Okay,
So
Yes,
here
okay,
I
sir.
wrote Sn as the set of bijective maps from 1 to ... 10 to itself. And you people told me that any such function can be written as product of cycles. So now I am asking you to go back to the language of functions. So to check if two cycles are equal, we have to check the associated functions are equal, right?
Yes, sir.
So now what is this cycle evaluated at 1 equal to?
it's 2.
2, sir.
Exactly. Yeah, so this evaluated at 1 is 2. What is this product evaluated at 1 equal to?
Also 2.
Yeah, that is because you have to evaluate a composition of functions, right? So now this function evaluated at 1 is 2, and then you plug 2 into this function, but this fixes 2. So in total, 1 is sent to 2. Now do this for 2 and 3 to check the equality of these two things. Is that okay?
Yes, sir.
Yes, sir.
Okay. Now, An is the subgroup of Sn consisting of such functions, which can be written as a product of even number of transpositions, as you told me. Okay?
Yes, sir.
It's a group. It's a subgroup because lengths, I mean, if you take two elements which are which can be written as a product of even number of transpositions, then their product is definitely an element which can be written as an even number of transposition, right?
Yes, sir.
So it forms a subgroup. Okay. These are really interesting. These are really interesting properties. So let me tell you one of the properties of An. So if you start with any sigma in Sn and any tau in An, I might ask the question, sigma tau sigma inverse, does this belong to An? This is a question. So what's your answer?
Yes, sir.
Yes, sir.
Yes, it does. Because tau has even number of transpositions, and it doesn't matter what the number of transpositions sigma has. It's doubled, right? Because sigma and sigma inverse, they have the same number of transpositions in them. So this is again even. So this says that if you conjugate any element of An by any element of Sn, which means doing this operation, you land back inside An. This is a really interesting property of subgroups, interesting enough to warrant a name. And this implies
Normal subgroup.
yeah, An is a normal subgroup of Sn denoted by this. Okay. So essentially all normal subgroups arise as kernels of homomorphisms. Okay. You saw what a kernel of a homomorphism is. That exhausts all normal subgroups in the world. Okay. You might learn this later, but it's okay. So normal subgroups. And I mean, this pair is really interesting because essentially when n is large, n is greater than or equal to 5, An and the trivial subgroup are the only normal subgroups of Sn. Okay?
Okay.
Yeah. And N doesn't have any proper non-trivial normal subgroup. It's called simple. That property of not having proper non-trivial normal subgroups is called simple.
Okay.
Okay. Now, starting with G and a normal subgroup, which is usually denoted by N for normal, one can construct a different group. Can somebody tell me what that is?
Quotient group.
Quotient group.
Yeah.
Factor group.
Yeah, the quotient group factor group, G mod N. And what is this? As a set?
Connection of all right cosets.
Yeah. The collection of all right cosets is denoted by NG such that G is in capital G. Okay. Now, this is just a set, nothing special about N has been used over here. Even if N was not normal, you could look at G mod N as the set of right cosets of N in G. But for this to get a group structure compatible with the group structure on G, you must demand N to be normal. Okay, it's a small exercise to see why the normality of N is needed. N normal in G implies this is a group in a canonical way. By which I mean this is a group in such a manner that the map from G to G mod N sending little g to NG is a group homomorphism. Okay?
Yes, sir.
Yeah. Now, let us move on to some theorems. Okay? Isomorphism theorems. How many are there?
Three.
Three. What's the first one? You can tell them in any order. Doesn't matter.
G by
If
kernel F is
G by
isomorphic.
kernel F is isomorphic to f of Z.
Yeah. So G by kernel F is isomorphic to
F of G.
image of F, which is also called F of G. There's the slogan, but I believe that you can all fill in the gaps what this means. What's the second one?
If H and K are subgroup of G, such that as H is normal subgroup, then HK by H is isomorphic to K by H intersection K.
Yes, this is isomorphic to K mod H intersection K. So yeah, if you drop this normality, then this is true as sets. But if you assume this normality, then this is true as groups. Fine. And what's the third isomorphism theorem?
H and K are normal subgroup. Then G by H divided by K by H is isomorphic to G by K.
G mod H mod K by H is isomorphic to G mod K. Okay? Yeah. So everybody knows what these isomorphism theorems are, right? Just keep these isomorphism theorems in your mind. You have to internalize them really well because in higher studies, nobody calls these first, second, third isomorphism theorem. These are just natural. If you see a homomorphism, then image is isomorphic to G mod the kernel. Nobody even calls them anything. Okay? You need to be really thorough with these. Then let's move on to Syllo's theorems. Is there a question? Sorry, I'm missing out on these questions. Oh, okay, fine. How many Syllo's theorems are there?
3.
Yeah. So what's the first one?
If p raised to the power r divides a group of order, then there exists a subgroup of order p raised to the power r.
Yeah. So classically, Syllo's theorems, the first one is if p to the n times m is the cardinality of G with m comma p having nothing to do with each other, then there exists a subgroup which we may call SP of G of order p to the n. Okay, that's the first Syllo's theorem. There are variations, but let's fix this to be the first Syllo's theorem. Okay. The second theorem, I mean, if you want existence of subgroups of any prime power order, then you just have to look at centers of these p Syllos. The centers necessarily grow, as you might know, and then you can pick out subgroups of whatever order you want. And the second one is, can somebody tell me what the second Syllo theorem is?
All the SPs are conjugate.
Yes. All SPs are conjugate by elements of G. Okay, which means if you start with SP prime, then there exists a little G, such that G SP G inverse is SP prime. Okay, please stop me if this is fast. Okay, we can go slowly.
Sir, actually, we are not taught Syllo's theorem, so we are not able to.
No, it's okay. It's okay if you don't know this. We can learn these right now. So the first one is Syllo subgroups exists. Then the second one, I'm telling you the morals. The first one is Syllo subgroups exist. Second one is all Syllo subgroups are conjugate for a particular prime P. Okay. And is that fine? These two?
Sir, SPs are Syllo subgroups.
Yeah. Okay. Let's see. Let P be a prime. Let G be a finite group. Of order P to the n times m, where there is no P in m, which is usually written as the GCD of m and P is 1. Okay. Then a subgroup H of G is called a P Syllo subgroup if the cardinality of H is equal to P to the n. Okay. So Syllo P subgroups are P groups. Their cardinality is a power of P, but the highest possible power of P, which it can have. By Lagrange's theorem, we know that order of H divides the order of G. And if we force H to have cardinality of P power, then what's the largest thing that it can be? P to the n. Okay. So this is called a P Syllo. It may exist or may not exist. But one of Syllo's theorems is that it does exist. Okay. The
Yes,
first
sir.
theorem is Silo P subgroups exist. Then one might want to classify them. This is a step in that direction. All Silo P subgroups or all P Silo subgroups of a finite group G are conjugate. So what does this mean? It means that given any SP, SP prime subgroups of G which are P Silo, there exists a little g in capital G such that G SP G inverse equals SP prime. Is that okay?
Yes, sir.
Yeah. Sometimes the alternate version of this is taken to be any P subgroup of a group G is contained in a P silo. But yeah, you can go between many statements. Okay. What's the third and the most important Silo theorem as far as numerical things are concerned? Numerical questions in JAM. It's that if NP is the number of distinct P silos in a group G. Okay. Remember that G has cardinality P to the N times M. I'll write it again. In brackets, cardinality of G equals P to the N times M. Then NP divides, this is a number, it divides M, whatever is left, and NP is congruent to 1 mod P. Okay? So remember this.
Okay.
So one instance where this is used is, when all three theorems are used is, if you start with a group of order 10, G be a group of order.
Excuse me, sir.
Yeah.
Sir, can you please let's know what is the basic meaning of conjugate?
What?
What is the basic meaning of conjugate, sir?
Yeah,
I did not
this second
know
line,
about this.
this one.
It's okay.
Yeah, maybe what's missing is that is I comma I dot E. That is this. Okay.
Okay, sir.
Yeah. Now let's see how Silo theorems are used. Let G be a group of order 10. Then there exists a 2 Silo and a 5 Silo, right? How many
Yes,
5
sir.
silos are there?
Only one.
Yes. N5 is what? Let's use third theorem. N5 has to divide whatever is left in the group. So write 10 as 5 power times whatever is left. So write 10 as 5 times 2. So then N5 has to divide 2. N5 has to divide 2 and N5 has to be congruent to 1 mod 5. So what's the only solution to this?
1.
Yes, this implies N5 is 1. Okay. Now, we know that all P silos are conjugate. So it turns out it's equivalent for a silo to be normal and NP to be 1. So N5 is 1. This implies S5 is normal. Okay. Because if you conjugate S5 by any element, you would get a subgroup of the same cardinality, right?
Yes, sir.
The cardinality of G S5 G inverse, given any G in capital G, the cardinality of G S5 G inverse is the same as the cardinality of S5, but the cardinality of S5 is the largest possible 5 power which lies in the group. Therefore, so does the cardinality of this. Therefore, G S5 G inverse, you can verify it's a subgroup and it is a 5 silo again. But you know that N5 is 1. So G S5 G inverse has to be equal to S5. There's only one 5 silo. So this means G S5 G inverse equals S5, which means that S5 is normal. Okay?
Yes, sir.
Yeah. So this is one way how this is used. Now let's do some quick finishing of the theory, and maybe we can go towards problems. So does anybody know what a G set is? Okay, so
No, sir.
yeah,
No,
so you
sir.
can look at a group. G is a group, and let X be a set. Okay, now suppose you have a map from G cross X to X. So you have seen an example. If you take X to be G itself, then you have a map from G cross G to G. Okay. This is a G set if, so this map is usually denoted by G dot X. Okay. Brevity sake, call it G dot X. If some conditions are satisfied, so the conditions are G dot G prime dot X is the same as G prime dot X. This is associativity, something like the associativity condition, and E dot X equals X. The identity acting on any X is just X. Okay. You can go and read what a G set is, but I'm just flashing this information in front of you. Then one can look at the orbits of an X in capital X. Okay, the orbit of an X in capital X, which is defined to be set of all Y in capital X such that there exists a G in G with, or such that G dot X equals Y. Okay, this is the orbit. Then one can look at the stabilizer of an X in capital X. Can somebody tell me what this should be? Common sense?
Inverse kind of.
So what does stabilize mean? So this is an action, right? We are letting G act on X by this thing. So what does stabilizer mean?
Maybe Gx equal to X.
Exactly. So set of all G in capital G such that G does nothing to X. G stabilizes X. Okay. Okay.
Yes.
Yeah. So now orbit stabilizer theorem says if G and X are finite, then there is a bijection between orbit of X the cardinality of orbit of X is equal to the cardinality of G divided by the cardinality of stabilizer of X. Okay, that's it. So that's the theory part of the lecture complete. Now let's move on to the theorems. Any doubt till this point?
Sir, can you go to the 6th page?
6. Okay, 6 is here.
So previous 5th page.
What?
5th page, sir.
Oh, 5th. Sorry. 5th, yeah.
Sir, somewhere you said even transposition, even permutation, product of even permutation and odd permutation is, you mentioned it even permutation.
No, what I said is over here, tau is an even permutation. It's a product of even number of transpositions. It doesn't matter what sigma is. Sigma can be an odd permutation, but it is paired with a sigma inverse, right? So in total, you have 2 copies of an odd number, which is an even number.
Okay.
Okay. Yeah. So let us move on to some problems. Is that okay?
Yes, sir.
Yeah, I hope these problems are here. Okay. So there are lots of problems. We have to run through these now. So can somebody tell me the solution to problem 1? So I'm looking at the quotient group Q mod Z of the additive group of rational numbers. So Q is a group, Z is a subgroup of Q. Then this is a quotient. Now 2 by 3 plus Z, is an element in Q by Z. What is its order? Everybody knows what order is?
Yes, sir. 3.
Yes, sir.
Yeah.
Yes, sir.
What is an order?
Number of elements in a group.
Yeah, but what is the order of an element?
Its power where it becomes 0.
Yes. So the number of times you have to do the group operation on the element with itself to make it identity, to bring it to identity. So if you add this element thrice, you get to 2. 2 plus Z, right? Which is Z, which is the 0 in Q mod Z. So the answer to question 1 is 3. Is that fine for everybody?
Yes, sir.
Yes, sir.
Okay. I'll run through these, and if you have doubts, please stop me. It's not at all rude to stop if someone is going fast. Okay. What about the second question? Let G be a finite group whose order is not divisible by 3. So the order of G can be 4, 5, 8. Is it true that for every G in G, there exists an H in G such that G equals H cube? What's the idea?
Not, sir.
No, sir. For
Okay.
the
So let's
identity
look at what?
for the identity element E, you can't find an H. Not for every group. It is not divisible by 3.
What?
Like if we take the element 0 in Z2, you might not find an H such that H cube is equal to 0.
Yeah, but so what does H cube mean in an additive group? It means 3 times
3
H,
times
right?
H.
3
Yeah.
times H. Exactly.
Yeah, 3 times 0 is 0, right?
So H need not be a different element.
No, it's not said it. There exists an H. So, what's the answer?
Yes,
Why?
sir, because identity is H is मतलब non-identity element, sir. Hello.
Yeah.
Sir, is H is non-identity element?
Well, no, it's not said in the question, right?
So we can take identity.
So so you're saying for every G, you can take H to be identity.
Sorry.
Sir, in Z2 we'll find one will not have any element in Z2. We can find that
How
will
about one?
one cannot be written as 1 plus 1 plus 1. If we do in Z3, 1
Yeah,
plus
but
1 plus
the
1
order
is
of
0.
Z3 is
3.
yeah. Is it divisible or not by 3?
Sorry, sir.
Yeah. So let us see. Let us follow some naive idea. Look at the homomorphism F from G to itself given by little g goes to G cube. Okay. Is this a homomorphism?
Yes, sir.
Really?
Yes, sir.
Yes, sir.
G is not assumed to be abelian. So the question is GH cube. Is it the same as G cube H cube? It may not be, right?
Yeah.
Yes,
Yeah.
sir.
But let's just assume for the time being that this happens. That this is a homomorphism. Okay. Now, what do you know about set theoretic maps between finite sets? So if you have a finite set G and a map from G to itself, then the map is injective if and only if it is surjective, right?
Yes, sir.
In the question, you're asking if the cube map is surjective. Right? Given any G, can it be written as a cube of something? So you are asking if the cube map is surjective. Then you might as well check if the cube map is injective. Okay? So now, is the cube map injective? So G going to G cube, is it injective? Injectivity of a homomorphism can be checked by computing its kernel, right? Yeah. So what is the kernel of F? It is the set of all G such that G cube is identity. Means the kernel is all elements of order 3. Okay? All elements of order 3. But now use the fact that G is a finite group whose order is not divisible by 3. Therefore, there cannot be any element of order 3 in G. Okay?
Yes.
Yeah.
Yes, sir.
There
Yes,
cannot
sir.
be any element of order 3 in G, which means that this map is injective, therefore the map is surjective. Okay?
Okay.
Yeah, but the issue with this proof is that this map is not a homomorphism. So what do? You know that this map will become a homomorphism if G is abelian,
Yes, sir.
right? So now, given any little g in capital G, you can look at the cyclic subgroup generated by little g inside capital G. Okay. Now look at the cube map from cyclic subgroup generated by G2 itself. Okay. Now the proof works. Therefore, to find this edge, you only need to look at powers of G. Okay.
Yes, sir.
Is that fine for everybody? Is there any doubt?
No, sir, no doubt.
Okay. There's a different proof. Everybody knows Piso's theorem? Piso's theorem in number theory. So, if n and m are co-prime, then there exists integers. These are integers a comma b in z such that na plus mb equals 1. Okay. Now take m to be 3. So if n is the cardinality of G, which is co-prime to 3, then there exists a comma b in Z such that na plus 3b equals 1. Now raise this to the power G. Therefore, G power na plus 3b equals G. Now try to finish the proof. Okay. Is that fine for everybody?
Yes, sir.
Okay. What about the next question? Among the additive group of rationals, the multiplicative group of non-zero rationals, and the multiplicative group of positive rationals, which pairs are isomorphic? We need to be quick. So let's start with the first pair, Q plus and Q star dot. Are they isomorphic?
No, sir.
No, sir.
Why?
No, sir.
Why? Just a quick answer.
In Q plus there exists only one element of finite order, and in Q star dot there exists two element of finite order.
Yes. In Q plus, there exists a single element of finite order, and Q star, there are two. So you can say -1 is the distinguishing element, right, between these. What about Q star dot and Q greater than 0 dot? What about these two? A quick answer again.
They are not.
Why?
सेम जो प्रीवियस रीजन क्यू स्टार के पास दो एलिमेंट है और क्यू ग्रेटर देन जीरो उसके पास एक.
Yeah. So is that fine for everybody? That Q star has an extra element of order 2. It has an element of order 2, which Q positive does not.
Yes.
Now, what about the first and the last one? Yeah.
Maybe it's not.
Yeah, no maybes. You're mathematicians.
Sir, it's not because Q plus has a finitely generated subgroup and Q positive dot not.
Why not? All powers of 2. That's a finitely generated subgroup inside Q positive, right?
Okay, sir.
Yeah, so let me give you the answer. In Q plus, given any number m in Q and n in natural numbers, there exists an element m prime in Q such that n times m prime equals m. Is that okay?
Yes, sir.
Which means the multiplication by n map, this means adding, doing the operation on Q n times this is surjective, right? Is that the case with Q positive?
Don't know, sir.
So take n to be 2. So now take m. Okay. So now let's ask the same question inside Q positive. So 5 is inside Q positive. Okay. And n equals to this is a natural number. Now, does there exist an m prime in Q positive such that m prime added, m prime square equals 5? Does there exist a rational number whose square is 5?
No, sir.
Yeah, that's the reason. Okay. The multiplication by 2 map is surjective on Q, but the same map on Q greater than 0 is not. Okay. Therefore, they cannot be isomorphic. Now, these are two opposite ends of a certain spectrum. This Q plus satisfies this property that for every m and n, there exists an m prime, such that n times m prime is n. This this should be interpreted as m prime plus dot 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 plus m prime n times. Okay. So this property.
Okay, sir.
This property, if a group satisfies this property, the group is said to be divisible. So Q is a divisible group, and Q positive, this every element in Q positive can be written as product I goes from 1 to k, pi to the power alpha I, where pi are primes and alpha I are integers. This property, if a group satisfies this property, then the group is called a free abelian group on these many generators, all primes. So this is a free abelian group and this is a divisible group. They are somehow on the two opposite ends of a spectrum. Okay. So now using this, using the fact that Q positive can be written in this way, can you answer question 4? So let Q positive upper 2 be the subgroup of Q positive consisting of rational numbers A by B with 2 not dividing A and 2 not dividing B. Is this subgroup isomorphic to Q positive? What is the guess? Maybe I'll tell you the answer. The answer is yes. And how do you prove this? So every element of Q positive can be written just like this. Product I goes from 1 to K Pi alpha I, where Pi are all primes except 2. And now you can take the shifting map. Okay. So I'm leaving this to you. You can try and figure this out. This was a question asked in one of the TI for interviews or exams. So yeah, there's that. What about question 5? Let P be a prime number. What is the order of SL2 Z mod PZ or SL2 ZP?
P into P square minus 1.
P into P square minus 1. How did you come with this? Yeah, the answer is correct. The answer is P times P.
By the homomorphism.
Yeah, how?
And there exists a homomorphism between GL to ZP and to UP. Then the kernel of this homomorphism is SL to ZP.
Yes. So what is this? This is the determinant map, right?
Yes, sir.
And kernel of the determinant map, this is exactly SL2 ZP. So now apply the first isomorphism theorem. So therefore, GL2 ZP modulo SL2 ZP is isomorphic to UP. Okay? Is that fine? This
Yes,
implies
sir.
This implies the cardinality of GL2 ZP equals the cardinality of UP times the cardinality of SL2 ZP. This is what? What is the cardinality of UP?
P minus 1.
Yes, this is P minus 1. What is the cardinality of GL2 ZP?
P square minus P multiplied by P square minus 1.
Yeah, let me write it as P square minus 1, P square minus P. Okay. Everybody knows how why this is true? Yeah, so I'll flash through the proof, but you can just memorize this. You don't need to go through the proof. The proof is that any element of GL to CP is a 2 cross 2 matrix ABCD. Now, how many choices are there for the first row? A has P choices, B has P choices, so P square choices, but these cannot both be 0. So therefore, you take away that choice, P square minus 1. And once this row is fixed, for the matrix to be invertible, its rows need to be linearly independent. So the choices for CD are essentially P square minus all the multiples of AB, and there are P multiples of AB. So therefore, P square minus P choices for the second row, P square minus 1 choices for the first row. Okay, just a flash of the proof. Now, therefore, the cardinality of SL to CP is this divided by P minus 1, but you can see P square minus P is P minus 1 times P. So from that, doing some algebra, you can get this. Sometimes this is written in a beautiful manner like this: P minus 1, P plus 1. It's an NPR kind of a thing. Now, what about question 6? Let f and g be functions from r minus 0, 1 to itself, defined by fz equals 1 by z and gz equals z minus 1 by z. What is the order of group generated by fg under composition of functions? To answer this question, one trick, I'll tell you a strategy to answer this question. So, first, prove that every element in the subgroup generated by f and g can be written as f power a times g power b for some a, b in integers. Okay? First, try to prove this if this works, and then you can just compute the order of f and order of g. Okay? Now, if order of f equals 2 and order of g equals 3, then how many different elements can you get out of this subgroup? So let's start by writing down some of them. So f to the power 0, g to the power 0. This is 1, which is the identity. Then the next one is f power 0, g power 1. Is that fine? Next one is f power 0, g power 2. You might want to write f power 0, g cube, but this wraps back to f power 0, g power 0, right? Am I
Yes,
making
sir.
sense?
Yes, sir.
Yeah. So this is not a new element. Then you can start by changing the power of f. f1, g0, then f1, g1, f1, g2. Can you write f1, g3? What is f1, g3?
F1Z0.
Again, f1, g0. Right. Now, what about here? f2, g0. What is f2, g0?
F0Z1. 0, 0.
Yeah, f0, g0. So, looks like these are the only elements, right? Is that okay? If
Yes,
this
yes.
statement is true, that every element in the subgroup generated by f and g can be written as a power of f times the power of g, and orders are bounded 2 and 3, then these are the only elements in the subgroup. So now, can you tell me, suppose this statement is true, and instead of 2, the order of f is, let's say, x and order of g is y. Then what is the cardinality of the subgroup generated by f and g?
It's xy.
It's x times y. Perfect. So you're getting the idea. So now your exercise after going home is to show that every element can be written this way. Okay, and a strategy to do that is to ask, what if you have an element like this, GF? Then the strategy is to see if you can write it this way. So you can definitely write it this way, F inverse GF, and then ask the question, can this be written as F times G power A for some A, or maybe I'll say C. Okay, is that okay? So this is a small exercise.
Can you explain that once more?
Yeah. So till this point, it's fine, right?
Yes, sir.
Yeah. So all that I'm saying is to prove this statement. So how do you prove such a statement? Every element can be written as F power A, G power B. So the first question you should ask is, what about GF? If I say that every element can be written as F power A, G power B, then I should be able to write G times F as F power A, G power B. Right?
Yes, sir.
So one way that this is possible is to look at this equality. So GF is definitely equals to F inverse GF. Is that fine? Because F and F inverse cancel each other.
Yeah.
So now you have a power of F here. Now all that you need to check is F inverse GF. Is this a power of G?
Okay.
If this turns out to be a power of G, then you are done, right?
Yes, sir.
Then if this is true, if question mark equality is an equality, then how do you write? Let's say FGF. So FGF is again an element in the subgroup generated by FG. I want to write FGF in terms of powers of F times powers of G. How do you write?
It's if F square G to the power C.
Yes, perfect. So write this as F times GF, but you know that question equality is an equality, which means that this is true, which means that GF can be written as F times G power C. So this is equal to F square G power C. Okay.
Yeah, got it.
So are you convinced that every element in the subgroup generated by F and G can be written as F power A, G power B once this is checked? So after this lecture, try and check this. What about the next question? Let G be a finite group with an automorphism P from G to G such that Pg equals E if and only if G equals E. Is it true that the additional condition P square G equals G forces G to be abelian? This is a slightly difficult question from one of the oldest, one of the old papers, old JAM papers. I would ask you to go ahead and solve this on your own. And if you have any doubts, you can ask me. Okay, I won't solve this for everybody in the lecture. Is that fine?
Okay,
Yes, sir.
Yeah. Maybe I'll give you a hint if you need. Okay, now come some easy questions. The total number of non-isomorphic subgroups of a group of order 17 is. What's the answer?
1.
Be careful.
2, sir.
Okay.
Yeah, 2. What is the reason? 17 is a prime. So the only group up to isomorphism of order 17 is
17.
yes, Z17. And it has exactly 2 subgroups, the trivial subgroup and the entire group. Okay?
Yes, sir.
Yeah. The number of automorphisms of a cyclic group of order 24 is?
Sir, can you repeat the explanation for eighth one?
Yeah. So the point is that there is a single group of order 17 and that is Z17. Okay? Now
Okay, sir.
17, the reason 17 is a prime. Now 17 is a prime means Z17 exactly has 2 subgroups. The trivial one and Z17 itself. The subgroups have something to do with the divisors of this number.
Okay, sir.
Okay?
Okay, sir.
Yeah. The number of automorphisms of a cyclic group of order 24 is?
8, sir.
Yeah, what is the reason?
Because automorphism of it's a cyclic group, so it is isomorphic to Z24. And automorphism of Z24 is isomorphic to U24.
Yes.
And cardinality of U24 is 9.
Yeah, why is that? So you said ought of Z24 is isomorphic to U24 and cardinality, I'll write it as Z24 star maybe. It's the okay. And what's the cardinality of this group?
8.
Yeah, it's the Euler phi function applied to 24. Everybody knows this?
Yes, sir.
Yeah, Euler
Yeah.
phi applied to 24. Now, how do you compute this? By prime decomposition. This is 2 cube times 3, which is the same as phi of 2 cube times phi of 3. What is this? This is 2 cube minus 2 square times 3 minus 1. This is 4 times 2 equals 8. Okay, that's the answer. Now, what about 10? The subgroup of Sn generated by this transposition 1, 2 and this cycle 1, 2, dot, 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 n is
Sn, sir.
yeah. Why? Yeah. So you have to remember this important formula that if sigma is an element of Sn, then sigma, then a cycle A, B, C, dot, 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 A prime, B prime, C prime, dot, dot, dot. This and sigma inverse equals sigma A, comma, sigma B, comma, sigma C, dot, 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 sigma A prime, sigma B prime, sigma C prime, dot, dot, dot. Is that okay? Does everybody understand what this means? This is a
Yes, sir.
really important formula which you should
Yes, sir.
always remember. So, suppose you have an element which has this particular cycle decomposition of Sn. Sorry, cycle decomposition in Sn. And suppose sigma is a different element of Sn, possibly different. Then the conjugate of this huge element by sigma in this order. So first apply sigma, then the element, then sigma inverse. This is exactly equal to this. Okay. So now, can somebody tell me what this is? 1, 2, dot, 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 n, 1, 2, then 1, 2, dot, 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 n inverse. What is this? By using this formula, so you have to take this to be sigma. This is sigma inverse. Then you have to write down sigma of 1 comma sigma of 2, right? Just blindly applying this equality. I need responses from you.
Yes, sir.
Yeah. So just blindly applying this formula, take this to be sigma, take this to be the middle cycle decomposition of an element, and this is sigma inverse. What is this? This is equal to this sigma evaluated at 1, sigma evaluated at 2, and so on, right?
Yes, sir.
So it's this. Now, what is sigma of 1?
It's 2.
Yeah. And what's sigma of 2?
3.
Yeah, 3. Now try to play around and see if you can make all transpositions out of this. Okay?
Okay, sir.
The point is, using this, you can make all kinds of transpositions and then Sn is generated by that. Now the question is, what if we replace 1, 2 by a different transposition? What about the subgroup generated by 1, 2, 3, 4 and 1, 3 in S4? What's the answer? So if you apply a similar trick to it, what do you get? If you conjugate 1, 3 by this, means if you compute 1, 2, 3, 4 times 1, 3 times 1, 2, 3, 4 inverse, what do you get?
It will be 3, 4.
You get 2, 4.
Correct,
Because,
sir. 2, 4.
yeah, 2, 4. Now, if you again conjugate 2, 4 by 1, 2, 3, 4, what do you get?
1, 3.
1, 3 back, which is not the case if you continued over here. So now, can you work this out?
Yes, sir.
If the subgroup of S4 generated by these two, is it the full group? Is it something smaller? Try to work it out. Then 11th question. Is it true that if every proper subgroup of a group G is cyclic, then G is abelian? What is the answer?
No, sir.
Why?
Quaternion group.
Yes. So everybody knows what the quaternion group is?
Yes, sir.
Yes.
Yeah. Please stop me if you don't know anything. It's okay to not know things. Yeah. You have to stop me if you are not getting some things. Okay. So quaternion, let's call that group Q8. How many elements does it have?
8.
8 elements. What are those? I can write it as 1 minus 1, I minus I, J minus J,
minus J, K
A
minus K.
minus K. What are some of the famous relations in this group? The relations are I square,
I, J,
A square.
I
A square,
square
K
equal to
square.
Yeah. Then IJK is minus 1. Then IJ equals K.
yes,
JK
sir.
equals I.
I
KI equals
equals
J.
J.
What about JI?
Minus K.
minus K.
Yes. And so on. So you can write down many relations in this group. Turns out all proper subgroups of these groups are cyclic. They are either Z1, Z2 or Z4. But the group is not abelian, as you can see. Ij is K, but Gi is minus K.
Yes, sir.
Now, is it true that if every subgroup of a group G is normal, then G is abelian?
Then quaternion.
No, sir.
Yeah. The answer is
No,
no.
sir.
And the counter example is the same group, quaternions. All the subgroups of this group are normal, but still the entire group is not abelian.
Yes.
Okay, fine. Now, next question. Is every group of order p square for prime p abelian?
Yes, sir.
Yes, sir.
What's the reason?
Yes, sir.
What's the reason? Yeah, so this is a fact coming out of the orbit stabilizer, I mean, not orbit stabilizer, but yeah, you can prove this out of some conjugacy classes that if G is a P group, then the center of G equals the set of all little g in capital G such that for all G prime in G, G prime equals G prime G. This center is not just the identity. Okay. Now, if cardinality of G is P square, then there are two possibilities for the cardinality of the center. Center is a subgroup, so its order must divide the order of the group. What are the divisors of P square? They are 1, P and P
P
square.
and P square.
But this fact says that the cardinality cannot be 1. So this cardinality is P or P square. If the cardinality is P square, if cardinality of ZG is P square, then ZG equals G implies G is abelian. But if the cardinality of ZG equals P, then one fact is that ZG is normal. ZG is a normal subgroup. So you can look at cardinality of G mod ZG. This is P. So therefore, G mod ZG is cyclic. Implies G is abelian. Okay?
Yes, sir.
Yeah. So this case cannot happen is the point. ZG cannot be equal to, the cardinality cannot be equal to P. Otherwise, some things break. So there is just a flash of the proof. You don't have to remember the proof to crack jam. But just remember that every group of order P square is abelian. Okay? What about P to the n for n greater than or equal to 3?
Start to
Is a group, is there a non-abelian group of order, let's say P cube?
quaternion groups.
Yes, sir.
Yeah. So it's not forced that every group of order P to the n for n greater than or equal to 3 is abelian because of quaternions. Quaternions cardinality is 8, which is 2 cube.
Yes.
Next, let H be a non-discrete subgroup of R comma plus. Now comes some topology in this. Find the closure of H in R with the usual topology. So what's the answer?
Sir, what is usual topology?
Euclidean topology.
सर इसके बारे में भी नहीं पता।
Yes, sir.
So the point is, if H is a subgroup of R comma plus, the positive real numbers, then either H is cyclic or H is dense. If
Oh,
H
okay.
is a subgroup of R, then there are two possibilities. Then H is cyclic or dense. You can try to prove this by looking at H intersection 0 comma infinity. Okay?
Yes, sir.
Everybody knows what infimum, supremum, and all of these things are, right?
Yes.
So you have to look at the infimum of the set H intersection 0 comma infinity. If that infimum is positive, then H is cyclic. If the infimum is 0, then H is dense. Now,
Yes.
cyclic are discrete. So if you are looking for non-discrete subgroups, then the possibility is dense, right?
Correct,
The
sir.
only possibility is dense. So then what is H bar? The closure of H in R.
R.
Yes. So a subset is dense if and only if its closure is R. I mean the full space. That's 13. What about 14? Let G be a non-abelian group and N a normal subgroup of G. Is G mod N cyclic? What's the answer?
Awesome.
No. Because you can always take N to be the trivial subgroup, right?
Yes, sir.
Yes, sir.
If you take N to be singleton identity, G mod N is isomorphic to G, but G is non-abelian, so it cannot be cyclic. What if we assume G is abelian or cyclic? So if G is abelian and N is a normal subgroup of G, is G mod N cyclic?
Awesome.
Yes, sir.
Again, no, because you
No.
can take N to be the trivial subgroup, N to be singleton identity. Then G mod N is G itself, which is just abelian, it may not be cyclic. Right? But what if G is cyclic? What do we know about cyclic groups? Subgroups and quotients of cyclic groups are?
Cyclic.
Cyclic.
Yeah. So that's what we have to use.
Yes, sir. That's why it is cyclic.
Yeah, that's why G mod N is cyclic. Any generator of G works as a generator for G mod N. Next, let G be S3. Find an element in G, direct sum G of order greater than the orders of elements of G. Can you do this? So, I'll tell you a formula. If F, comma G, these are elements of G, then order of F comma G inside G cross G. Now, this is an element in G direct sum G. Order of F comma G in G direct sum G is the LCM of orders of F and G. Okay.
Order of G. Yes, sir.
So now, what is the largest order of an element in G? G is S3.
3.
3. So orders are 1, 2, and 3 in S3, right?
6.
So the largest is 3. Now, yeah, how do you get an element of order 6?
An element of order 2 and order 3.
Order 3. Yes, sir.
Yes. 2 comma 3. The LCM is 6. What if we change G to S3 direct sum S3? Then can you find an element in G direct sum G whose order is greater than the orders of elements of G. Try to work this out on your own. Okay?
Yes, sir.
Okay. Question 16. Is Z3 direct-sum Z3 isomorphic to Z9?
No, sir.
No,
Why?
sir.
Z9 is cyclic and Z3 cross Z3 is not.
Yeah. So can you, using what we learned in question 15, can you tell me why there cannot be an element of order 9 over here?
Yes, sir. There is no element of order 9 in Z3, direct sum Z3.
Yeah. What is the reason? Because orders of elements over here are LCM of order of element here and order of element here.
Yes, sir.
Can you make the LCM 9?
No, sir.
Yeah, you cannot. 9 in German. Okay. What about Z7 direct sum Z5?
Yes, sir. ये हो जाएगा.
Yes, because LCM of 7 and 5 is
35.
35.
Yeah,
35.
exactly. So producing an element of order 35 over here, like producing a subgroup isomorphic to Z35 over here, but then by cardinality reasons, this has to be isomorphic to Z35. Okay. Next, let G be a group. Alpha and beta in G be elements of orders 4 and 6. What is the order of alpha beta? Can you say?
It's 12.
We can't say, sir.
No, sir.
Why? Why not? Okay, can you cook up some elements A and alpha and beta which have finite orders, but alpha times beta has infinite order?
Yes, sir. जो जनरल लीनियर ग्रुप से हम बना सकते हैं ऐसे मैट्रिसेस.
Yeah, so what are the matrices? They have some number theoretic significance also. Or I mean the counter example has some number theoretic significance. So let me tell you the example. This is really interesting. To take G to be SL2Z. So this has many interesting properties related to modular forms. Now, in this, you can take alpha to be 0, -1, 1, -1, and beta to be 0, 1, -1, 0. Now, can you tell me what's the order of beta? It's 4, right? Because if you square beta, you get minus identity. You have to do this quickly. But
Yes,
what
sir.
is alpha beta? You can later check that alpha has the right order, but you can believe. Maybe I messed up the order, but fine. What is alpha times beta? Let's compute. So 1, 0, 1, and 1, right?
Yes, sir. Correct.
What is the order of this element? Yeah. The order of this element is infinity, right?
Yes, sir.
Yes,
What
sir.
is alpha beta square? If you multiply this matrix with itself, what do you get?
1201.
Yeah. If you multiply it thrice, you get 1031, 4 times 1041, dot, dot, dot.
Yes, sir.
Right? So this matrix has infinite order. But yet its constituents have a finite order. Order of alpha is 6, order of beta is 4. Okay?
Yes.
Sorry
Okay,
for
sir.
that typo. Here, alpha and beta should have the other orders. This should be 6 and this should be 4. Yeah. So in number theory, the transpose of this matrix is important and this matrix is important. They are, they are closely related to modular forms. Now, what is the remainder when 5 to the 2025 is divided by 11? How do you compute this?
By congruento.
Yeah, the congruence arithmetic. So, what can you tell me about 5 power 10 mod 11?
One, sir.
Yes, what is the reason?
5 power 5 is congruent to 1 model 11. So it's just a square. So it's also congruent to 1 model 11.
Yeah, but there's a cheating way of doing this. And the
Fermat's
cheating way
theorem.
is, yeah,
Fermat's theorem. There is a theorem.
which theorem?
Fermat's theorem.
Fermat theorem.
Fermat's theorem. Yeah. It's called Fermat. So 5 to the power P of 11, that is congruent to 1 mod 11. What is P of 11?
Will be congruent to A mod P. Fermat's theorem definition.
Yeah. But this, this is a way to prove it. This is a slightly more general version of the other theorem. This is basically the fact that order of an element divides the order of the group, if you try to look at it that way. 5 is an element inside U11, right? What's the cardinality of U11? It's Euler-Phi function applied to 11. So this fact is just a repackaging of Lagrange's theorem. Now, what is phi 11? 5 power 10 is 1 mod 11. But yeah, you even went ahead and computed 5 power 5. So 5 power 5 is 1. Therefore, 5 power any multiple of 5 is also 1, right?
Yes, sir.
Yes, sir.
And that's the point. 5 power any multiple of 5 is 1 mod 11. Next, find an element in S5 with the largest possible order. Can you cook up an element of order, let's say 6? Forget largest possible order, but order 6.
Yes, sir.
How?
Sir,
It's
2,
2.
3.
At 2, 3.
2, 3, 4.
Yeah. So the way to do this is you have 5 symbols 1, 2, 3, 4, 5. So you want to write down cycles just like this 1, 2, then 3, 4, 5. Now use the fact that these two commute. What do we know? Cycles, disjoint cycles commute, right?
Yes, sir.
Disjoint cycles commute. Therefore, 1, 2, and 3, 4, 5 they commute. And therefore, order of this is LCM of orders of 1, 2, and orders of 3, 4, 5. Okay. This is 2, this is 3. That's how you get 6. Okay.
Okay, sir.
So you might come across S, let's say 35 or something. You want to find elements with large orders inside, let's say it's 35. So you have to partition 35. You have to look at a partition of 35 and take LCM of the numbers appearing in the partition. Okay.
Okay, sir.
That's how this is solved.
Yes, sir.
Next, the number of group homomorphisms. There's a typo again. Sorry. The number of group homomorphisms. There should be an S over here. From ZA to ZB is
GCD of A,
GCD
comma
of AB.
perfect. So hom ZA, comma ZB, the cardinality is GCD of A, comma B. The reason is any homomorphism is determined by the image of 1 in ZA. 1 has to go to X such that order of X divides order of 1, which is A, and order of X divides the cardinality of ZB, which is B. This implies order of X has to divide GCD of A, comma B. And associated to each such divisor, you get distinct homomorphisms. So therefore, number of group homomorphisms from ZA to ZB is GCD. Now, the subgroup of Sn generated by all three cycles is
AN.
Yeah. So let's end here that the subgroup of Sn generated by all three cycles is AN. Everybody knows the reason? The reason is, here's the hint, you can try to prove it yourselves, that in Sn, you will encounter even product of even number of transpositions, right?
Yes, sir.
So they will look like they will look something like this: AB times CD. Now you have to argue what happens if these are all distinct. If AB and CD, these are all distinct, then you write it this way. So product of 2-3 cycles. But if they are not all distinct, suppose B equals C, then what is the product? You can compute and you can check it's a single 3 cycle, okay?
Yes, sir.
Right. So maybe that's where we'll stop today. I have this sheet consisting of 74 problems. Maybe I'll add some more problems to it and we'll solve all of these problems, let's say, in the next lecture. Hopefully.
Yes. Thank you so much for such a wonderful session, Anand sir. And for participants, next session will be on day after tomorrow, that is on Friday, 10th of January, from 6 to 8 p.m. as per the schedule. Thank you. Thank you.
Yeah, thank you for
sir.
listening and sorry for going over time.
Thank you so much, sir.
Okay.
Not a
Thank you,
problem,
sir.
sir.
Thank you so much, sir.
Thank you, sir.
Thank you.
And where we get our recorded video, sir?
Hello, participants. We have been getting a lot of requests for recordings of the lectures. As such, we'll not be sharing the recordings to you all, but we'll soon upload it in our YouTube channel. The details will be shared to everyone. Okay?
Okay, ma'am. Thank you.
Thank you, ma'am.